Thank you very much. Can everyone hear me with the mic? Perfect. My name is Matteo Luisi. I'm a graduate student at West Virginia University. What I would like to talk to you about today is a project that I've been working on for a while now with my advisor, Lauren Anderson, and our collaborators, Dana Balser, Tom Bania, and Trey Wenger. And it's about H2 region ionization of the ISM, where we did a case study on one particular H2 region, which was NGC 7538. I just want to mention the paper for this project was just accepted, so if you're interested, please check it out. It's on the archive. And let's start. All right, so the main question we're trying to answer here is, how does the warm ionized medium maintain its ionization? Now, Matt Hafner gave a really nice introduction about the WIM about an hour ago, so I'm just going to skip that part. I just want to say that since the WIM is a very large component of the ISM, there has to be some sort of ionizing radiations that's constantly being pumped into the WIM so that it can maintain its ionization. So supernovae definitely contribute to that, but if you do the calculations, it turns out that they just simply don't fulfill the total energy requirements. It's the general consensus now that O-type stars are the main components that provide these ionizing photons that are being pumped into the WIM. But there are some questions that still remain partially unanswered. If O stars are responsible, these photons have to travel through the H2 regions around the O stars. They somehow have to travel through the PDRs, so either they travel through the dense PDRs themselves, or the PDRs must be clumpy and may have holes in some directions. So there's still a lot of work to be done here. Previous work shows leaking photon fractions for single H2 regions between 25 and 60%. But most of these regions were extragalactic, they were very energetic. So what we want to do here is we want to focus on one compact H2 region in our galaxy and see what we can find. Our case study is on the region NGC 7538. It's very nice to study because it's in the outer galaxy. There's very little confusion at a galactic longitude of about 111 degrees. NGC 7538 is compact. It has a diameter of about 5 parsecs. And what we do is we use radio continuum observations with the Green Bank telescope to estimate the leaking radio continuum emission fraction for this region. And we also use radio recombination lines from the GBT to estimate properties of the leaking emission and the radiation. I just want to point out this project would probably not have been possible without the Green Bank telescope, now that their budget seems fairly threatened. So what we want to do first is we need to define a boundary around the H2 region so that we can define emission inside this boundary as being associated with the region and emission outside that boundary as being leaked. And that boundary is the PDR. So what we do here in this image, that's a 12 micron image from the WISE data. This is nice because in 12 microns we have emission from PAS that can highlight the PDR. You can see this bubble-like structure around the region. And we can trace this bubble visually to define an inner PDR, which is the solid white line in here, and an outer PDR, which is the dotted white line around that. What we also see is a second PDR-like structure to the east of the region, this arc here, where we have increased 12 micron emission in this arc and very little emission outside. So this is our radio continuum image of the region. The white contours start at 0.01 kelvins and logarithmically increase to 5 kelvins, just so you can get some information about these faint lobes you have on the sides right here. But you can also see that most of the emission is fairly centrally peaked here. So here we just plotted the PDR on this map. You also see these green circles. These are the locations of our radio recombination line measurements. and the beam size is consistent with the size of the circles. So what we did here is we defined the inner PDR boundary as our boundary where emission outside will be classified as leaked and emission inside will be associated with the region. We basically perform simple aperture photometry. And for this case, we find a leaking emission fraction in radio continuum of about 15%. It might be worth noting that this emission fraction is a lower limit just because of the three-dimensional geometry of the region, because we do not see emission, leaked emission in front and behind of the region, because here along the line of sight, it's superimposed on the region itself. So this may artificially decrease the leaking emission fraction by a bit. We also repeat this analysis for H alpha, and here we find a slightly higher emission fraction of 31%. But keep in mind that this leaking emission fraction is still mostly lower than those fractions found for larger H2 regions in other studies. What you see in this figure here is the ionic number abundance ratio of helium to hydrogen. Each of the points in this figure corresponds to one of the green circles, one of the positions of radio recombination lines that we did, that I showed in the last figure. And each of these points are located along a line in the figure on the previous slide, on the line of constant galactic latitude. So what we see here is that the ionic number abundance ratio stays fairly constant within the region, but we do see a decrease in these upper limits to the east. So these indicates that for some reason helium ionizing photons are being suppressed in that direction outside the PDR. So we effectively see a softening of the radiation spectrum here. To the west of the region, we unfortunately did not detect hydrogen, so we cannot say anything about the upper limits there. We also look at dust temperatures of the region. This is a dust temperature map from the Herschel-Hovis program. Again, you see the PDR that we defined in the infrared image. And this white contour here shows a constant dust temperature of 23 kelvins. So hotter dust is inside and colder dust is outside this white contour. What you see here is that we see a very rapid decrease in dust temperature on the west and on the south of the region. This indicates that the PDR may be very strong in these directions. But we do see dust enhancement further outside the PDR to the north and to the east. But we also see that this second PDR over here to the east effectively blocks these higher dust temperatures. And outside the PDR, dust temperatures are lower. Now that we have all these properties about the region, we'd like to compare this region with a much larger, more energetic H2 region. And the region we picked for that is W43. We have a lot of radio recombination line data for W43. So what you see here in these two plots is just the hydrogen line strength of our radio recombination lines around the two regions. What we do here is we fit these line intensities for select directions, just because we cannot assume that the H2 regions are completely symmetric. And if we do that, we see that the line temperatures decrease much faster for the smaller region than for the large region W43. So if you compare this fitted line profile, we're almost at 0 millikelvins at a distance of about 10 parsecs from the compact region NGC 7538. But when we look at that distance for W43, we have much higher emission, and it takes about 200 parsecs for the emission to decrease. So this suggests that small regions cannot effectively, photons from small regions cannot effectively travel these large distances that would be required to maintain the ionization of the WIM. To summarize, we observed the compact region NGC 7538 as a case study, so we could investigate whether compact regions can can be responsible for ionizing the WIM. We find a leaking emission fraction in our radio continuum data of about 15%. This is lower than previous studies suggest for larger regions. We see that the radiation in the helium ionizing spectrum seems to soften outside the PDR. We also notice increased dust temperatures, but these are also very much confined by the PDR, either by the inner PDR that we defined before or by the outer PDR in the other direction. So all these suggest that small, compact H2 regions are simply not as effective in sending ionizing photons far into the ISM as larger, more energetic regions are. A project that we would like to do in the future is to repeat this analysis for a more energetic region. We're thinking about the W345 complex. It's in the outer galaxy. It's bigger. So this might be a good case study for that. Thank you.
Ed. Softening of the radiation field outside these H2 regions, in fact, looks to be a fairly general result. We looked at several and find exactly the same thing, that the ionized helium to hydrogen abundance ratio is low, like 0.02 to 0.03. And so I'm not sure, I've been scratching my head how to understand this, and I haven't come to any sensible conclusion. I'm not sure whether you have either, but I'd be glad to hear it if you have.
So we have not investigated this much further because our focus on this study was mostly whether the ionizing photons effectively reach the WIM far away or not. But it's definitely something that we'd like to do in the future, to look more closely into the softening of the radiation field.
One more from Matt in the back.
This is a really good study. I'm really excited to see this kind of stuff right now. What I'm wondering is, what about the source itself, and what do you know about it? And have you been able to do an accounting, basically, of what can you do an accounting of how much ionization you see versus what you expect from the source, for example?
So we have done a photon count, and we have a general idea that there are 3 or 4 sources within that region, and we have a general idea of what their classification is. But we have not done any calculations further than that.
All right, let's thank Matteo again.